This is Jimbo. I'm from University of Southern California. This is a joint work with my colleagues, Chuanghua, Mukun, and Chou. Many people became aware of such channels after spectral and meltdown attacks were reported in 2018. They affected a wide range of x86 processors by causing information leaks through timing set channels. In addition to timing set channels, there are many other types of set channels, such as power, sound, heat, EM emission. In this work, we are more concerned with power set channel. Consider this following encryption algorithm, which takes the plain text as input and generates ciphertext as output. The crypto key is stored in the device as a secret. Without set channel information, it would be hard to reverse engineer the key. However, if given set channel information, such as power consumption, it would be easier to infer the secret. Specifically, the adversary observes intermediate variables through power set channel and exploits the dependency between intermediate variables and the secret to retrieve the secret. The dependency is where the leakage comes from. What we expect to have is a sound set channel analysis, which takes the encryption algorithm as input and generates either the detected leakage or the fully verified guarantee. However, manually designing such analysis can be labor-intensive and cannot adapt to new changes. What we actually want is to automatically generate set channel analysis from data. We expect that there are some works already which you can learn or sound static analysis from data. However, it turns out that none of them could guarantee the soundness. In addition to the lack of soundness, some of the existing works even require expensive deductive reasoning. Therefore, can we automatically and efficiently learn a sound static analyzer from labeled training data? It sounds ambitious, right? Here comes our idea. We will introduce the overall framework and the learner and prover respectively. Our goal here is to develop a powerful synthesis framework, which takes the training programs and type annotations as input and generate a sound analyzer as output. Now let's demystify this powerful dinosaur framework. It consists of two parts interacting with each other. Our new idea here is really about introducing a prover to check the soundness of the learned analysis. The learner learns candidate analysis rules and feeds them back to the prover. The prover either validates analysis or rejects analysis and returns counterexamples to the learner. We firstly take a closer look at the learner. The learner also consists of two parts interacting with each other. Feature synthesis part applies SIGAs to generate recursive features, and the rule synthesis part applies decentralized learning to generate analysis rules based on those features. Now you might be wondering what the analysis rules look like. We firstly introduce training programs. There are two ASD nodes representing two intermediate variables. The input nodes are assigned with the predefined types. The UKD type represents that the input variable is secret and potentially vulnerable. The in-rand type means that the input variable is random. All the input variables will be assigned types initially. The random type means the intermediate variable is random. The type inference rules are used to infer the type of all the intermediate variables. We firstly apply rule 1, and we can infer the type, and then we apply rule 2, we can infer type one level further. Here, we will not go into the low-level details of the rule. Instead, we focus on the learner. Our rule synthesis part makes its first attempt and generates a new tree. The red path leads to a node where two different types are grouped together. It is due to the fact that the current feature set is insufficient for distinguishing B4 and N1. Therefore, we invoke the feature synthesis part to generate a new feature with a higher information gain in order to assist the rule synthesis part. After receiving the newly synthesized feature, the rule synthesis part makes a second attempt and generates a new tree. We take a closer look at this new tree. Each node has been correctly classified. However, is this the analysis we want that can soundly infer the types? Actually, we are not sure either. To resolve this challenge, we introduce a prover to check the soundness of the learner. If the prover rejects the current analysis rules, it will provide counterexamples as feedback to the learner. The interaction between learner and the prover keeps iterating back and forth until starting from the IC iteration, the interaction finally terminates when all the rules are proven to be sound or it reaches a time bound. Till now, we got a general overview of the synthesis framework and the learner component, but the prover component still looks mysterious. We only know it either fully verifies the programs or generates counterexamples. Let's demystify what's inside. Inside the prover, there are two parts, knowledge base and query containment checking. The first question coming to your mind may be, what is a knowledge base? It consists of two sets of proof rules, one for propositional logic and one for distribution types. Our core idea here is to prove that the learned rule can entail the proof rules in KB. Here, I will not bore you with the details of KB. Since both KB and our learned rules are expressed in data log, the entailment checking can be reduced to the query containment checking, which is to check if the set of relations defined by our learned rule is also contained in the set of relations defined by KB. Here, I will use the diagram to demonstrate our idea. The black circle represents the whole universe, which consists of all the variables. The green circle represents the safe region defined by KB. The complement of the safe region is a vulnerable region. The green dashed circle represents the safe region defined by our learned rules. As long as the green dashed circle is inside the green circle, we can prove that our learned rules are sound. This may sound intuitive, but still ambiguous to you. We highly recommend you to refer our papers for more details. We developed the powerful dinosaur framework to learn a sound analyzer to avoid the human work. To evaluate its effectiveness and efficiency, we are going to answer the following three research questions, which are actually about the performance of the synthesizer framework and the performance of the learned analysis. Our benchmarks are cryptographic programs collected from public source. They are divided into training set and test set. In terms of the performance of the analysis, our learned analyzer is 266 times faster than the manually crafted analysis. In other benchmarks, the running time of our learned analysis is also much lower than the manually crafted analysis. In terms of the accuracy, we can almost achieve the same accuracy as the manually crafted analysis. In terms of the performance of the learner and the prover, the running time of each iteration is less than 1 second, which is pretty efficient. The number of rules produced in each iteration also remains modest, which is more likely to generalize. To summarize, we propose the first data-driven method for learning a sound static analyzer. We guarantee the soundness by solving a data log query containment checking problem, and our learned analysis can effectively detect such channel vulnerabilities. Thanks for listening to our talks, and I'm happy to take any questions.